Good morning, everyone, and welcome back to this course on environmental bioethics at St. Thomas University in the Masters of Bioethics, beginning always with a little prayer. In the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you for all your many blessings, for the gift of life, for having us here today. We ask that you send your Holy Spirit to illumine our hearts and minds so that we may delve into the issues of environmental bioethics according to your divine will as we seek to care for our common home, in the words of Pope Francis, to take care of the environment, to be good stewards, particularly in this topic today on population growth and human population growth, extremely complex and complicated issue, that you may guide us always according to your divine will. We pray always in a special way for those who are in most need of your divine mercy. In the name of Christ our Lord. Amen. Son, Holy Spirit. All right, so always asking if there are any questions or comments from previous lectures, anything in the course, in the program. No, we're going to move forward then. And just to review briefly, let me dim the lights here. Okay. We started looking originally at the formation of the Earth in the geosphere, and then move forward with life on Earth, thanks to the liquid state of water, which is the basis for organic life here, because we see that that metabolism takes place within this soup of at the cellular level and all the way to the level of the entire organism. Then we looked at the atmosphere, the hydrosphere, and we looked at cycles in nature. And last week we focused on energy and the different energy sources and how we are seeking, the powers that be, let's say, especially those who are concerned for the environment, trying to shift from fossil fuels to renewable energy sources, which are varied, but they are complicated issues, yet we see that a number of nations in the world have made a big commitment to this, so they're moving slowly but surely in that direction. Now we only have 2 more lectures left, this one and next Saturday, so the topic for today is going to be population succession in nature and then population growth in general, some basic principles there, and then human population growth and population density, all right? And then finally, next week, we'll look at the whole claim of climate change and how that is panning out. What kind of evidence do we have for or against it and the consequences of that. Okay, so moving now into population, we're going to see 2 aspects. We're going to see what is called succession, natural succession, how species succeed each other in nature, and then focusing specifically on population growth, including human population growth, right? And then finally, looking at some bioethical issues there, and directives or guidance that we have from our Catholic teaching. So moving forward then in succession, we see that there are basically 3 stages of succession globally, overall 3 stages of succession, okay? First, what is known as pioneer species or pioneer stage. Then there is going to be succession as such, species that succeed one another in this intermediate range, all right, where succession as such happens. In other words, literally species replacing each other both in the animal kingdom, the plant kingdom, and also fungi and bacteria, but we're going to focus mostly on animal plants, which is what we can see, and it's typically what is above the ground, okay? And then finally, the last stage is called a climax community, when all the succession stabilizes and there is no more succession. The ecosystem it stabilizes, and unless there is a drastic or significant climate change, it will remain, that ecosystem will remain as it is, with a variety of plants and animals, fungi and bacteria that it has, and that is what we call a stable ecosystem, all right, with its particular biodiversity. So that's an overall view. We're going to get now into a few more details. So again, this is in nature, all right? And it's interesting because you think about it philosophically, of course, in the scientific world, we do not accept that there is a guidance, if you will, or that there is a predisposed order, right, or a finality or a teleology, right, as far as telos being a goal. We saw that with Meyer since the first semester when we covered Ernst Mayr, and he made that point very clearly, that nature essentially just happens. Mm-hmm. And so in the scientific world, meaning the empirical world, it's not accepted that there is a preordained order that is going toward a particular finality. Rather, nature is just happening by its own laws, but they do accept at least that there are laws. So that's where my understanding, the door is cracked open, if you will, for posing the claim that there is one who orders, because otherwise there has to be a legislator to have these laws, these natural laws, right? And we believe that those natural laws do come from divine law. And so for believers, we can compaginar, we can dovetail, or we can harmonize the facts of nature as we observe them with our beliefs that there is an author of life and there is an author of the universe. At any rate, we see that these succession stages occur in whatever environment there is, as long as we need two elements for succession to occur, all right? We need the biotic factors. In other words, we need some species around to begin with. And we also need the abiotic factors, the non-biotic, meaning the conditions, the necessary physical conditions for life to occur. So just to review, what are those physical conditions? The abiotic factors, the non-biotic factors, right? The non-living factors. 3 or 4 of them that are so evident that we even forget that they exist, that they allow for the possibility of life, again, on Earth. So what are those abiotic factors? Light is one, light or lack of light, right? So that makes a distinction between day and night, for example. We can already think of behaviors, day behaviors and night behaviors of animals and plants also, right? Okay, so light or lack of light is one. Water or humidity, or water in some state, because water can be either ice, liquid, or gas, all right, vapor, water vapor, and all those have an impact on life. Air itself, which goes beyond water, it is the atmosphere that we're breathing, okay, including the gases, the gas component of that air. What other factors are significant and necessary for life? Soil. So the mineral content of the soil, right? That's non-biotic. In other words, minerals are not living in themselves, but they provide the nutrition necessary for plants and also for animals. Temperature is another one. That narrow temperature range for life which is from where to where, more or less, in centigrades. The range, the temperature range for life on Earth. The coldest, about 5 centigrade above, because once we get to freezing, then essentially the cell freezes and there's no metabolism. Metabolism is shut down, right? So about 5 degrees centigrade, more or less, which is the average temperature of the bottom of the ocean floor at depth, and all the living creatures that live there in that, what we would consider very cold weather, right? 5 centigrades. And then on the upside, on the hot side, about the hottest that we can normally tolerate.
42?
Around 40, 42, exactly. So we round it up to about 40. So you consider from 5 to 40 is about 35-degree range, temperature range. Very tiny when we compare the extreme heat and the extreme cold that occurs in the universe. It's a very tiny range that we happen to have, in great part because of the distance to the sun and also the angle of incidence and all that allows for that temperature range, okay? Okay, so these are like the background or necessary abiotic factors for life to occur. So now let's focus on the biotic factors from now on. I'm going to be focusing on the biotic factors and more specifically on the plant kingdom, all right? Because those are the ones that provide sense. Why are plants the basis for life at the organic level on the biotic factors? Exactly, photosynthesis, which makes them producers, right? Producers. They're able to transform light energy into chemical energy, which is stored in the glucose molecule in carbohydrates, and that is potential energy that can be used for recharging the ATPs at the biochemical level, meaning allowing for the possibility of metabolism, for energy to be available for metabolism, right? Because light energy as such doesn't cause any metabolism directly, right? But the trigger is that photosynthesis. And that's why I'm focusing mostly on plants on this succession story. All right, so starting with the pioneers. Pioneers typically are plants that are able to establish in a barren area. A barren area meaning could be rock, sand, soil. Those are the 3 basic ones, okay? I'm talking on land. Something similar happens in the ocean also, but I'm going to focus on land mostly. So a barren area is first colonized by these pioneers. And typically they're small plants, and the most common ones are mosses and lichens. And particularly lichens, all right? Because lichens are what is known as a symbiosis. And it's very interesting, lichens, because there are symbioses between fungi and algae, right? Which are generally fairly primitive organisms. But one is a producer and the other one is a consumer. So let's look at these lichens. You've seen them around. They're fairly common, especially in humid areas, tropical, subtropical, even temperate areas. And the lichen is a symbiosis, is mostly a fungus. The structure is mostly a fungus. But a fungus, remember, are fungi consumers or producers? Fungi. They belong to a kingdom of their own, right? And so they're not plants. Do they photosynthesize? Just the fungi by themselves. Mushrooms. You see the mushrooms on the entrance there, little white caps?
I think they're consumers.
They're consumers because they don't photosynthesize. Therefore, they're not producers, and not producers, they have to be consumers, all right? In other words, they don't produce their own food, meaning their own carbohydrates, and therefore they have to be on the consuming side. But they're a particular type of consumer, all right? They're certainly not carnivores in the sense that they don't eat other animals. They're not even herbivores as such. They don't eat plants either. What do they eat?
Organic material.
Organic material. So they are this third category that is called saprophytes. Remember the saprophytes? Saprophyte, S-A-P-R-O, right? Saprophytes, meaning that they love decaying material. They love rotting stuff. Sapro is a reference to rot, and phyte is love, all right? Philia. So saprophytes are those who love rotten stuff, and they continue to rot it, to break it down until nutrients start coming out of that rotten stuff, and that's what they absorb, and that's their nutrition, okay? The whole other domain that does that is the bacteria, of course. And thank God for fungi and bacteria in the world, otherwise we'd be buried in organic material, decaying organic material over the millennia and over the billions of years, right? Okay, so that's the fungus itself, which typically are not green because they don't photosynthesize. But then, over time, this symbiotic relationship has developed whereby some fungi have been invaded by algae inside their tissue. And inside the tissue, it's a good thing for algae because algae typically, do they live in dry or wet? Wet, exactly. Algae are aquatic, many are marine, some are freshwater, but algae need to be hydrated, they need to be in the liquid environment. And so that's what they find inside the fungus, because the fungus is mostly maybe 80, 90, 95% water, I don't know exactly, but fungi are very hydrated. And their color, their tan color and so forth, they're semi-transparent. So they allow sunlight to go through their tissue, and they have a very hydrated tissue. So it's kind of an optimal environment for algae to be in there protected. And therefore, so that allows algae, some algae, to actually colonize land. Otherwise, they would have to be in a pond or in a lake or in the ocean. And this allows some algae that actually embed themselves into the fungus to live on land where there is not that much, not liquid water as such. But at the micro environment, there is. Okay, so these are the lichens. And so what does the algae provide? So we see that the fungus provides the algae essentially a habitat, a niche in which to live. The algae, just by reason of being so algae, are they consumers or producers?
Algae produces, they photosynthesize.
They photosynthesize, so they're producers, and therefore they're nice and comfortable in there, they're protected, and just by way of photosynthesis, as a payoff, let's say, they are providing actual nutrients to the fungus, all right? And so the lichens now are stable, and they have many different shapes, as you can see. Typically, they grow either on the bark of trees or rocks. But they also secrete certain acids. The lichens secrete acids. And so what does that do to the rock? Starts eroding it. Starts eroding it because rocks typically are on the alkaline side. Right? They're compacted and crushed minerals and so forth. So the acid from the lichens actually is eroding the rock little by little. And that erosion means at the microscopic level that some minerals start to accumulate there. And then as the lichens and the mosses themselves die, they provide also organic material, some nutrients, so that over time, with these pioneers, what will happen is they'll begin to develop a layer of a little bit of soil, of nutritional minerals, and an environment where other plants that are a little larger can grow in that area. So from a barren area, after the pioneers, other small herbs will start colonizing the area, okay? So the general tendency here is to go toward life, I make a simple analogy. Let's say that someday, God forbid, this building, for some reason, for whatever reason it may be, we move out of this building and it's no longer used. and centuries go by. So we have essentially a concrete structure that is going to start decaying, right? Breaking down, mostly because of the weathering, the sun and the wind and the rain will start cracking it up. But then also what it could be expected eventually of this building if we just leave it alone and walk away. Plants will start growing on it. Plants will actually start growing on it. And we can expect the first ones to grow on the concrete will be lichens. Okay, and mosses, particularly with the kind of human environment that we have, it's conducive to that. And eventually, this building will be covered with plants, vines, and so forth, all right? And in fact, we have that kind of succession in Latin America, in Central America, and also Mexico, what we call Mesoamerica. If we go back to not prehistoric, but actually to the ancient civilizations of the Mayas, the Aztecs, the Toltecs, all of these great civilizations that built pyramids and so forth, now they're all covered by vegetation. And in these places, which are typically, they tend to be flat terrains, you see these hills on the horizon. Well, underneath those hills, typically there is a pyramid that goes back 500 or maybe 1,000 years, all right? And we see it all over the place in Mesoamerica. And the work of archaeologists is precisely to denude those ancient structures from the vegetation that is on top of it. But that vegetation has helped to preserve it somewhat. But also sometimes you see even trees growing on top of these pyramids, all right? And those trees, of course, with their root system, they have dislodged and move around some of those large, huge boulders. So it's a plus and a minus. It has protected the structures from weathering of sun and rain, but at the same time, the life on it, especially the plants and trees, have also reshaped the pyramid somewhat, okay? So it's quite a bit of work, and it's labor intensive, as you can imagine, to dig out these places. All right, so there's a succession then. The second stage, which is varied, all right, and it progresses, is what is known as the intermediate species. They're going to be grasses, shrub, bushes, and in general, there's going to be a larger and larger size of plants that will establish in that area. Simply, it's a direct relation, if you will. It's a proportion to the amount of nutrients that are becoming available with time from the soil. All right, so as more plants colonize the area, eventually those plants will die and become broken down by the fungi and the bacteria into nutrients, and then larger plants can come into the area. Eventually you start getting trees coming into the area, all right, until finally we have some dominant species of trees that will establish there. Okay. When we get dominant species over a relatively long period of time, then that becomes what is known as a climax community. And this word community, I want to review it because it's a technical term, that is the third layer, if you will, right? We went from individual organism to a population, remember, in population biology. So a population, how do we define a population, biologically speaking?
Group of species?
Single species, group of individuals, okay? Group of individuals. So I say community is the third layer because the first layer is the individual organism as such, that to consider the species, again, remembering Meyer, who gives the biological definition of species, two things: that species, that individual organism, right, to belong to a species, needs to grow, metabolize, be alive, and secondly, to reproduce fertile offspring, okay? So that includes the progeny, includes the possibility of continued survival of that species. Okay, that's at the individual organism level. Then when we have two or more individuals of that same species, Now we're getting into a population, right? Then, so when we look outside of this wall, outside of this window, when we look at nature, we don't see just individual populations isolated, right? We don't see just a population of grasshoppers all clustered over here, and then the population of grasses all clustered here, and then the population of mockingbirds or whatever it's going to be over here. You know, they're intermingled, right? They're intermingled in what we call the community. So that's the community. The community is a cluster of populations that are coexisting. The fact that they're coexisting means that their niche and their resources are different. They're not competing for the same resources because of the competitive exclusion principle, right? If we have two populations of different species that are going after the same resource, let's say two species of birds, two populations of birds that are going after the same insect, right? Sooner or later, what's going to happen?
One of them are going to disappear.
Exactly. One of them will displace the other. In general, the stronger, the most able to catch those insects faster, earlier, etc., you know, will displace the other population. Those population will have to move elsewhere. Okay. But when we have a community, when we have various populations of different species interacting, it means that they're not going after the same resources. So it also speaks of the abundance of resources in an ecosystem that is able to maintain communities, to maintain different populations. Okay? So there's this flourishing, there's this abundance of resources in general that also may bring back memories of Darwin, and one of his observations that started him thinking about evolution is the overabundance, the overproduction of organic material. Like, for example, when fish lay eggs, they lay thousands or hundreds of thousands of eggs, and yet it only takes 2 of those eggs to be fertilized to replace mom and dad, right? And so there's an overabundance, and most of them either die or rotted and become nourishment for bacteria, or they're eaten by other fish, other species, etc. Okay, so there's always this overproduction. So these are basically the 3 stages, but the ones that are several stages of succession is in between here. There will be different types of shrubs and herbs and bushes, and some of them are annuals, meaning that they only live 1 year. Others are perennials, others are semi-annuals, and so forth. You have all these different classifications, okay? All right, so this is showing the whole section in a single shot, if you will. We start with the pioneer species, and you can see that they start getting larger and larger. Eventually, when we have trees entering the area, colonizing that area, then we start going into a forest situation. That forest becomes mature and then becomes stable, and that is the climax community. In the climax community, in the climax forest, you're going to have basically 1 or 2 or 3 main species of trees, of the largest trees, and in the northern temperatures or in the colder temperatures, they're going to be pine trees, they're going to be conifers. And then in the temperate and tropical and subtropical regions, they're going to be what we call deciduous trees that shed their leaves annually. Because you'll have basically, in the temperate region, you have the 4 seasons, right? Summer, fall, winter, spring. And then in the tropical regions, you basically have typically 2, there's a rainy season and a less rainy season, if you will, all right? And so the plants stay green all the time typically, or they shed their leaves at an individual basis, but there's greenery year round. All right, moving forward then, I wanted to point out here, this particular climax community, the photograph that I chose is a slash pine forest, which is what we actually have here at St. Thomas University. All right, so this is the slash pine, which has adapted to this region, even though it's a conifer, and already this should call attention to someone in the know that we have. For example, in this photo, you can see these are pines up here, but then look down here, what is known as the understory. Understory is everything that grows underneath the tall trees, underneath the canopy. What are these down here? Are they pines? Not pines, right? Are they, let's make it a little bigger. Are they trees? Are they shrubs? Look at the leaf. They're palms.
Oh, yeah.
See how they're palms?
Yeah.
Okay. Oh, I'm sorry, it's not too clear on the granular. Yeah. You see the palmate leaves? See how they're palmate, right? They're palms. So when we see palms and pines together, that's a very significant sight for people who know. Why? Because pines typically come from a cold temperature. They have needles instead of leaves. They have cones instead of flowers. They're adapted to cold temperature, even to ice, right? To frozen temperature. That's also why they're called evergreen, because in the winter, they're the only ones who stay green, and they have an advantage over the other trees that go dormant. But palms don't tolerate any degree of cold, right? They're tropical or subtropical climate plants. So to see pine and palm growing together is a very rare sight. And of the two, which had to adapt? The pine, because the palm cannot tolerate. That's why you don't see palms north, beyond a temperate region, you don't see palms. Even in the Carolinas already, you don't see palms, all right? And, but pines for sure, all of northern US and into Canada, huge acres of pine land. So the one who adapted was the pine. Okay, and that's why it's so unique. I'm always trying to emphasize this because we are privileged, we here at St. Thomas University are privileged to have this slash pine forest. This is an actual photograph of it, which you can see. This one of those Google satellite photos, all right? For example, here's the science building. That's where we are now. This is before the construction, which is going on here. So all of these pines, slash pines, were cut down, 27 of them. And they had a permit. However, we're trying to protect the forest, because you can see it's about maybe 1/3 of the property. In fact, this whole area here is about 30 acres, and the whole property is about 120. So it's maybe 25% of the property. And we're trying to preserve it because it is slash pine forest, and it's the last one, the highland. It's the last highland pine forest that is left in the county. There's more pine, the slash pine, in the southern part of the county, down toward Perrine and Homestead and that area, and the Redlands. But that is what is called a rockland pine, meaning that it actually grows on top of the rock, which is limestone, coral rock, all right? And it's more tenacious. That pine is the same species, slash pine, Pinus elioti, but it's actually even more tenacious because it's growing on top of limestone. But because it's growing on limestone and doesn't have that much soil, they grow very tall and thin and spindly. They don't grow massive like these do. These are known as specimens because they have at least 18 inches of diameter, 1.5 feet of diameter. For some of these trees, I can tell because I've been doing research in the forest for years, it may take 2 people to go around a single trunk, okay? Some of them are just huge. Their lifespan is about 100 to 150 years, so they were definitely here before the university was here. And that's all that's left of it. So we're trying to preserve it. Here's a specimen, not from our forest, but this is slash pine, Pinus elioti. Okay, and it's the only pine that has adapted here to South Florida in a subtropical environment. Okay, So now you understand what is known as succession in nature, is this replacement of species going bigger, larger, greater area. So in general, everything else being equal, it is expansive. If we were to leave it alone, the Earth would continue to replenish itself, and both on land and in the oceans, life would be thriving. There is this condition of life to continue to thrive into biodiversity and all this, right? Okay, so now we can look a little bit of stats or some quantification, which is growth curves. Any questions about this concept of succession in nature? Oh, the last thing I do want to point out is here, precisely, stable climate. A forest or any climax community will remain that way as long as the climate is stable. Now notice I'm saying climate and not weather, because the weather, what is the weather doing? The weather is changing all the time. The weather is dynamic. For example, the weather changes daily from light to no light every 24 hours, about half light, about half no light. That has a drastic effect, for example, on producers, because they're only producing half of the time on average on a daily basis, right? Okay, since it has an effect on the producers, it also has an effect on the consumers. Even behavior, there's daytime behavior and nighttime behavior for plants and animals. All right, then it changes on a seasonal basis, the weather, so that we have actual 4 seasons and so forth, right? So we can say that the weather frame is going to be on average what? Up to, time-wise, we can talk about weather up to a year's time because of the different seasons, all right? So the large frame, let's say, for weather is going to be 1 year on average, okay? Which synchronizes nicely with one translation, right, of the Earth around the sun, back to its original spot. Then when we start accumulating weather year after year, decade after decade, centuries and millennia, we start going into what is known as climate. But climate is always that long-term and climate trends, right? Is it getting warmer? Is it getting colder? Or is it stable, the temperature, over a long period of time? And also, is the average amount of humidity, rainfall, etc., about the average also? Those are things that determine climate long term, okay? And so we look at trends. So necessarily, when we're looking at climate, we have to go into statistics. Because, going back more than 3, 4, I don't know when the thermometer was actually invented, probably quite a few centuries ago. But let's say we go back 500 years or to the Middle Ages. Let's go back 1,000 years. That's only 1,000 years, right? Who was measuring the temperature 1,000 years ago? And where is it recorded? And what instrument were they using? No, none of that. So now we have to use indirect measures for that kind of, if we want to see temperature, which is a critical factor with regards to the global warming, right? We have to look at indirect measures. And what's the typical indirect measure that we look at? This is called paleoclimate or paleoclimatology. Well, one of the main, we're going to look at greenhouse gases in the atmosphere and their density, their amount, their percentage. And the main greenhouse gas by volume, not by heat retention, because methane retains more heat, but by volume is CO2. So that's why they look at ice cores, right? To go deep into Greenland, the Arctic, and Antarctica especially, into ice cores. And those ice cores, because they're layered, again, according to the season, they can determine the number of years or decades or even millennia, and then get samples of bubbles of CO2 in there that is mixed into the air. So imagine the sophistication of instrumentation that needs to measure that, right? But they're looking at the content, the CO2 content of the primitive atmosphere or the ancient atmosphere to make an estimate with a lot of error, margin of error, of what was the temperature at that time. Imagine. So it's a lot of heavy measurement and statistics and so forth, and the model is going to be as robust as the number of core samples that are able to take throughout the whole world, but there's no ice in the tropics, right? So it's limited to the caps and maybe glaciers that are up. That's why the glaciers are important for that perspective, is because you can have glaciers in the tropics or near the tropics. Like, for example, the Andes that have permanent snow way up there and can get maybe some ice cores even in the tropical region of the world, but very, very few spots. The other one that is much more obvious, of course, is the Himalayas, which are near to the tropic, but they have permanent snow, right, and glaciers. Okay, so you can see that this climatology and paleoclimatology is kind of a sophisticated science. That's how they're trying to estimate and then look at trends. After to do all that crunching, they'll look finally at a histogram and see where the slope is, if it's a positive or a negative slope, or if it's a neutral slope, right? It's totally horizontal. Okay. So now let's look at what is known as a typical population growth curve. Because we're looking at species that are replacing each other and are growing constantly, right, in abundance, in a radiating fashion. The typical growth curve is known as it goes by several names, a sigmoid growth curve, a reference to an S, because you can see that this curve, if you take an S and you pull it by its two sides, you get this kind of a curve, right? This kind of a shape. Just take a normal S and pull it by its two ends. You get this S-shape curve, which is known as a sigmoid growth curve, all right? And it has basically three phases. The start is called the lag phase. Then the middle is called the log phase. And finally, the top is called the stationary phase. Now, important to understand the axis here. What is it that we're plotting, right? What is it that we're measuring? So the independent variable typically goes in what axis? In the horizontal axis, in the x-axis. And that's why we have time, because time is an independent variable. In other words, time is going on whether we measure it or not. We're here, there, we could be, at Versailles having a cafecito, there's still time going on, right? So time is ticking no matter what. So it's a typical independent variable. Okay, so here goes time, and it's important to note that this scale here is linear, meaning that each individual segment of time is equivalent to every other segment of time, whether it's minutes, hours, centuries, or millions of years. 1 million year is equivalent to another million year. So it's a linear scale as opposed to a logarithmic scale, for example, right? So it's linear because the curve itself is going to follow a logarithmic progression, right? But the time scale is linear. And also the y-axis, what do we have? The y-axis typically holds or represents the dependent variable. And here the dependent variable is number of individuals of whatever species. Each species has a growth curve. From bacteria all the way to the sperm whale, which is the largest animal on Earth, all right? Every species on Earth, the 2 million species approximately that have been discovered and classified so far, they all follow some growth curve that, of course, is a natural growth curve, unless they are in a zoo or in a petri dish or something like that. Even in a petri dish, it would still be natural for the bacteria because that's their particular environment, okay? So, number of individuals. So why is this a dependent variable? It's dependent on what? On the passage of time, okay? That's the dependency. It's important to understand the concepts because otherwise statistics is just a bunch of formulas and procedures, but we don't understand why we're doing this. It's meaningful. The dependent variable has to be depending on something. In this case, it's dependent on the time passage. So we would expect with the passage of time, on average, the number of individuals to increase or decrease? To increase with the passage of time. We made the example of the building being taken over by nature, right? Okay, so, but this number of individuals, I want to point out and again, reinforce that it's on each species and on every species that we have discovered so far in nature, okay? They all follow the growth curve, and the typical growth curve, not always, but the typical growth curve is a sigmoid growth curve. So basically, what is the y-axis plotting? It is plotting the population, the increase in the population, right? Number of species, number of zebras in that patch of grass in the African Sahara, or the number of lions that are going after that zebra, and so forth. So these three phases correspond to what is limiting these three phases, basically the nutrients available, the food that is available, or in the case of plants, the other nutrients, typically light, for example, but also space. So that's what's going to limit a population. At first, we can say that the lag phase is kind of a slow growth. Typically, the progression is going to be a doubling of the population at every stage, okay? So for example, if we start on the asexual side with, let's say, with bacteria, they're reproducing asexually by binary fission or splitting into two, So one bacterium splits into two. Now we got two daughter cells, two daughter bacteria. So it's double the number, right? So we've gone from 1 to 2 in X amount of time. That X amount of time typically for bacteria is about 20 minutes, more or less, right? I'm talking about average. Particularly E. coli from the time of the lab research, that under ideal conditions, bacteria, E. coli in particular, duplicates or goes through binary fission every 20 minutes, which is rather fast when you start thinking about it. Within 1 hour, you already have 3 layers of division, all right? And because it is a geometric progression, right? The progression is geometric, meaning a doubling. A linear progression, what would be a linear progression? Starting with 1, by increments of 1. A linear progression is 1, 2, 3, 4, 5, it's linear, right? A geometric progression is nonlinear, it's not gonna give you a straight line, it's gonna give you a curve. And is the curve gonna go up or down? Originally, the curve is going to go up in a that's what defines a parabolic, because it's x to the square. Yes, it's doubling. So from 1, we're going to get 2 in the next generation. 2, then 4, 8, 16, 32, 64, 128. Okay, now 3 digits. Exactly. So you see, from 1, 2 is the first division, 2, 4, 8, 16, 32, 64, 138, 138, 128, thank you. So in 7 divisions, we have 128 individuals. in a geometric progression. In a linear progression, we would have how many individuals? Seven. So 128 versus 7 is a lot more in the same number of divisions. When you start continuing to double that population, by the time you get about 15 or 20, you're close to in the millions already, okay? And so that's it. That goes into what is known as a log phase or exponential, because it's logarithmic. It's doubling and it's x squared. So it shoots up very fast in a relatively short amount of time. So it starts slowly, but soon it picks up very fast. And in this first half of the curve, then we can talk about the sigmoid, split it in two, right? When it shifts gears, let's say, the first half then is parabolic on the positive side. What is determining the growth rate here? What is determining the growth rate? Yeah, nutrients for sure, but at this stage originally, the nutrients are in excess, right? There is excess abundance of nutrients or food material, etc. What is basically determining this growth rate, this time, is going to be the generation, the time of generation, which each species also has a time of generation. For example, bacteria, under ideal conditions, we said is how long? 20 minutes. How about for humans? What is a generation?
9 months?
No, a baby cannot reproduce yet.
Okay.
And cannot hold a pregnancy.
13, 15.
On average, about 20 years. A human population, a human generation, on average, globally is considered about 20 years. So it's a very different time scale, right? For bacteria, it's 20 minutes. For the human, it's 20 years. So for example, if we were plotting this for bacteria, this time, what would be the units for this time?
Minutes.
Would be minutes. Would be minutes, okay? Because within 1 hour, we're already into a very fast log phase. However, if it were for humans, we're plotting human population, this would be typically years. So the scale changes, right? The units change, but the concept is the same for each species. And each species has a particular generation time, whether it's a sperm whale, whether it's what happens to these parrots, las guacamayas, the beautiful parrots from Latin America, what happens with them, that they get neurotic and they start chewing on their claws, on their feet, because they last a relatively long time. Their lifespan of the guacamaya is, I think, around 80 years. Exactly. And so what happens with owners? They get sick and tired of them, or the owner dies before the bird dies, and so they go to another owner, all right? Or they go back to the pet shop, or they're resold, and so forth. And so what happens with the guacamayas, which they tend to be rather intelligent for the birds, they're realizing they're being passed from one owner to another, and they're going to get a different treatment from every owner. Some are going to be excellent treatment, some can be, they may not get enough water, the water is dirty, you know, so the guacamaya is going through all these different psychological stages of treatment, and they start getting neurotic over time, and they start chewing on the cuticle around their claws. And they start getting infections, and it's a mess. The poor things, simply because they laughed a long time. You know, this is one example of how it can have an effect, but just to point out that the guacamaya has a lifespan of about 80 years. Some turtles have a lifespan of about 150 years. Pinus elioti here has a lifespan between 100 and 150. It's a larger range, okay? So we can say about 125 years average. So each species will have a range. Some are very short, some are longer. In general, the larger animals tend to live longer, but not necessarily, or also with plants, okay? There are some sequoias. You've heard of Sequoia National Park in California, spectacular national park. I happen to be there. Sometimes did some camping, and these trees are huge, humongous. There's Colonel Sherman, one that has a name. To see the top, you have to go so far back, because if you don't see the top, you fall over. It's so tall. This guy is 2,000 years old and is still living, okay? However, it's considered a juvenile, and this is a sequoia is a type of a pine tree, it's a conifer. This is considered a juvenile at 2,000 years because the rangers, the park rangers, discovered one that had fallen in the forest, okay, and they measured the core, they measured the rings, the tree rings, and they measured from the core to the bark, they measured 4,000 rings. 4,000, of course, it's dead, it was falling over, but that one, before it died, was 4,000 years old. So it's amazing, the range, okay, of trees. Check out the scale. Cars can go under it. Look at this one, they have the whole team, see how many it will take to go around. There's Sherman. Yeah. Anyway, so
where is that park?
it's in California. It's one of the national.
It's close to San Francisco?
It may be, I think so. It's in the northern part of California. Has Yosemite is another one. California has several national parks. You know, not every state has a national park because it has to be a unique ecosystem. We have one in the whole state of Florida, which is our Everglades. Oh, I think now the coral reefs also has been declared a national park. Biscayne National Park, Biscayne Bay, which is an aquatic marine national park. Not every state has a national park, and that's a worthwhile trip. For example, when one retires to do the national parks of the US, it's spectacular. It's just overwhelming, beautiful nature. Anyway, all this to point out that every species has a population growth curve. Typically, it is a sigmoid curve like that. And then on the second half of the curve, on the upper part, what happens eventually with number of individuals increasing in the same general area, the resources are going to start to run out of resources. You know, there's only so many zebras that can be fed in that grassland, all right, of the grassland of the plains there in equatorial Africa, the savanna, and therefore the resources start becoming limited because we don't have unlimited resources. There are always limited resources, okay? Whether they're biotic resources like grass for herbivores or herbivores for carnivores. It's always a limited number. Or abiotic factors, typically the geographic space, the habitat. So at some point that population starts leveling off, okay? And it will stay level like that as long as the climate stays stable. It will go into the stationary phase and continue horizontal. Now, horizontal, what does horizontal mean on a histogram with time versus number of individuals? Horizontal means that time continues to pass by, of course, independently, but the number of individuals stabilizes. Exactly, stays the same on average, right? Maybe some noise, some wiggle on a yearly basis or seasonal basis, but it more or less hovers around the same number, the same range. What does that mean? Then the number of individuals that are dying are being replaced by the number of individuals that are being born or coming into that population. All right, so there's a replacement. It doesn't mean that they're all dying, and it certainly doesn't mean that they're growing without any deaths, okay? It just means that there's a dynamic equilibrium between births and deaths. All right, it's a dynamic equilibrium. And that's what stabilizes the curve. And again, as long as the climate stays the same, that curve will flatten out, in principle, indefinitely, until there is some kind of catastrophic or significant event that will happen. Okay, when those events happen, then we start getting extinctions. And if that event is catastrophic enough, we could get a mass extinction, all right? And it seems to be that we're heading towards the sixth mass extinction on Earth. Well, I'll hold that topic for next talk. It's going to be more relevant. But the things are getting challenging. All right, so anyway, that's the population growth curve that we've analyzed with these two phases or the three phases, but basically a fast, slow start, fast, intermediate, and eventually levels off when the resources are maxed out and it reaches a stable condition. All right. This is in greater detail, what I've talked about already, but this concept then is an important one, the carrying capacity. Every environment has a carrying capacity for every species that lives in that environment, in the community, okay? And that's the carrying capacity. So we can say the carrying capacity, for example, of these 30 acres of slash pine at St. Thomas University, the carrying capacity of this rectangle, it's about 200 slash pines. That's the carrying capacity. In other words, at some point, you can see the greatest density here. If all this area became dense with slash pine, what does it mean? That one canopy is next to the other, and that's it, and that's stable. Then what happens for new pines to flourish and break through the canopy, old pines would have to die and topple over and rot and so forth and create a clearing on the canopy coverage, allowing for new pines to come up, okay? So it would stabilize that way. And actually, it would be probably around 300 or so of these pines. That's the carrying capacity for that. Then we can do also carrying capacity for the understory, the number of palm trees that can grow underneath, and then the number of rabbits that can live in that particular environment, or foxes, or grasshoppers, whatever species you name it. All right, for each species in the community, there will be a carrying capacity. A carrying capacity. And that is studied a lot in nature, okay? What is the carrying capacity for each individual species for it to flourish and to continue living? So you can see, for example, there will be a carrying capacity for all the grasses here, which are various grasses that are living in here, different species, but this would be certainly a community, right? In this patch, it's a pretty dense carrying capacity for each individual species here, right? In contrast, for example, with these mountain lions or pumas, that you can see that the carrying capacity for puma in this, which looks like maybe the, what's that called, the Grand Canyon, all right? What are these guys? Are these herbivores or carnivores?
Carnivores.
They're definitely carnivores, and they're called top carnivores, right? They're at the tippy top of the pyramid. And remember, the trophic level is 10 times for each level. So you can imagine starting with whatever grasses are going to be out there, and then what is feeding the rabbits or the pika or whatever ground squirrels that are feeding on that grass and so forth, bring it all the way up to these top carnivores. It means that they're going to need a lot of terrain to survive, a lot of area. So the carrying capacity for the puma, let's say in the Grand Canyon, is going to be a very small number, all right? It's very flat, it's a small number. So each, let's say each mating pair or each family of pumas is gonna need quite a few square kilometers or square miles for survival because simply of that trophic level of accumulation of biomass to stay alive. If we have too many families of puma here, they're going to start competing for the same resources, and then the strongest family is going to dominate, and the other families are going to have to move out into other areas. We can see the same in an agricultural environment, all right? There's only so many cows that can be sustained in this particular patch of grass before this gets overgrazed, right? What is this? These are bacteria growing on the tip of a pin, all right? So that's the tip of a pin. Even though it pricks the skin, it's pretty blunt at the microscopic level. And these are bacteria, you can tell that they have not reached their carrying capacity, right? There's still a few bold spots that can be colonized, but eventually when they reach what is known as confluence, right? One bacteria next to the other, and that tip is totally surrounded by bacteria, that's maximum growth there. When that tip is confluent, it happens the same with the Petri dishes, right? Okay, just examples of each species has its own carrying capacity, depending on the environment where they are. Except for the human. In other words, we can learn empirically what is the carrying capacity for every other species out there that we have discovered, except for the human. We just cannot tell what is the carrying capacity of the human species on Earth. Okay? It's a big puzzle. It gets complicated. First, two things. First of all, we can talk about a global human population, meaning that for biological purposes, all humans on Earth, the 7.5 billion that we are, we're a single species, but in principle, we could all interbreed with one another, in principle. And so we are considered a single species, a single population on Earth, okay? Also because of our tremendous ability to move around. Of course, people with greater means have a greater capacity to move, but even these mass migration movements that have been happening since prehistoric time, we are a very mobile species. Even when we started mobility, which was bipedal walking around Africa and eventually out of Africa, this brings back memories from the other course, I hope, right? All the migration routes, remember? From somewhere equatorial Africa, bordering the coast into Asia and eventually into Europe, and then further eventually into Americas and so forth. And to this day, you can see that it more or less follows the higher density routes, okay? There's a map of density, number of persons per square kilometer, the highest being more than 500 in Southeast Asia, India and Southeast Asia, and a little bit in Europe, Northern Europe. At any rate, what we have is that we just don't know what is the carrying capacity of the human species for planet Earth. So one is this high mobility, meaning that we are a single species, a single population. Second is that we produce our own food, one way or another, by way of agriculture and animal husbandry, mostly agriculture, which in general we have become very successful, especially the more industrialized nations, the more developed nations, become extremely successful at agriculture, what is known as quaternary agriculture. Primary agriculture is basically just planting a seed, dropping a seed somewhere, and then allowing nature to grow it by rainfall, amount of light, and so forth. That's primary. Then when we start putting the seeds in rows and making a hedge around it to have water come through and a primitive like little channel, that's already some technological intervention to flow water to the seed or the seedling, even when there is no rain. That's already secondary agriculture. When we put more machinery on it and we start making dams, for example, and let the water flow at certain times of the day or so forth, that's tertiary agriculture. And so forth, we add layers of technological complexity all the way to the combines that I showed you in the previous lecture, where that fellow spends his or her whole day inside that machine that picks up the corn on one end and puts out the mulch on the other end with a husk, okay? The whole day in there, in air conditioning back and forth. That's already quaternary agriculture. Hydroponics, meaning growing crops just in water with nutrients, with no land. Can be inside a warehouse with artificial lighting, and we can now replicate basically sunlight with the qualities of the different rays. It is the dirtiest light, right? Meaning that it has the full spectrum of wavelengths on the light spectrum. That is, so most pure light is what? Laser beams that are a single individual wavelength, okay? That's the most pure light, and that's why it has the different colors of the rainbow. Specifically, you can bring it down to 3, which are the yellow, the red, and the blue. And then when you combine those between yellow and red, you get orange. On the other side, when you combine red and blue, you get purple or violet. And then when you combine blue with yellow, you get green. So the pure lights really are wavelengths. Well, each wavelength in the spectrum will have a pure wavelength, right? By Armstrong units, whatever is measured. But those are pure lights, pure wavelengths. So the opposite is impure, and the most impure light is white light, which has a full range of, it's kind of counterintuitive because we think of white being the most pure, but it's not. It's the most impure light, which is the sunlight, which has the full range of wavelengths, all right? Anyway, just a little aside. Basically, back to the carrying capacity, we just don't know. And so we have to analyze this because it happens that our human population growth is doing this, okay? Now, we're gonna analyze this in a few minutes, but I figured this is a good time to take a break. We've been going at it for about an hour and a half. And so why don't we take a little break here for a moment, all right? Any questions, comments? No? Okay, so we're gonna transition now in the second half from nature into the human nature and what's going on and the possible consequences of this kind of dramatic population growth curve, which we're still only on the first half of the sigmoid curve, all right? It's a very drastic sigmoid curve, as you can see. Okay, break time, let me pause this. Okay, welcome back everyone. So here we're going to the second half of this lecture today on population growth, growth curves, and specifically human population growth, and what does that mean bioethically, the impact on human population growth, considering that we are, for biological purposes, we're considered one population globally, all right, that we have been able to inhabit practically every place on Earth, including places like the Arctic, the poles, North Pole, South Pole, because of our technology and our ability to generate our own artificial environment that is capable of sustaining life, even in thin air, if you will, with the International Space Station, the ISS, that is orbiting the Earth and has a small population of astronauts on a regular basis for months at a time. So that's a drastic example. To me, the ISS is the most drastic example on how we have been able to conquer just about any environment, even no environment at all. Right? Oh. Okay, well, you've seen these photos, and that, by the way, is an international thing, and it has an ongoing camera that is live, and because it's being funded in part by NASA, which are public funds, we have access. It's a public domain. You can go into this website and you can see the camera going on. It's typically focused on Earth. And, yeah. Let me see. Yeah. They have their own site there. Yeah, it's going to be some Publicity. Yeah. No.
Just like.
So you can see it's moving. Okay. These are some screens down here. Where you see the Earth underneath here moving. And the camera is picking up part of a structure. Looks like some kind of antenna. And these look like panels. Whoops. I guess it goes up periodically. These are shots at night where you can see the night lights of great cities, of megalopolis actually, which we're going to be talking about. Interesting. So this is a live camera going on right now from the ISS, the International Space Station. And what you see here significantly, this is not just fuzz. This is not just that the camera is unfocused. This is the atmosphere. This is the layer of atmosphere, that thin blue, before we go into space, all right, that is keeping everything alive. And mostly the troposphere, the first 10 kilometers. Okay, then he's got some soothing background. It's going to put us to sleep, so I'm going to shut this down. Okay. Back to Earth, with the population growth curve of the human, which, believe it or not, this is a sigmoid curve, but more than a sigmoid, it looks like an L shape, right? An inverted L. It's so steep here. And what happened here? Well, we went into log phase, is what happened. So for the past 7,000 years, which is estimated, what happened 7,000 years ago? Jericho, basically modern civilization, or civilization began. Agriculture in the Fertile Crescent in the Middle East, between the Tigris and Euphrates, the two rivers that are today in Iran, Iraq, that whole area used to be Mesopotamia, Babylonia, and Jericho, for example, is one of the oldest cities in the world, in Israel. About 7,000 years ago, estimated to be the agricultural beginning of modern civilization. Agricultural beginning. The cultural beginning happens much later, around the year 500 BC, with classical Greece, right? But agricultural beginning. And so we see that this lag phase is rather pronounced when we look at the time scale, 7, maybe 8,000 years ago. Who knows when we began here? Well, we can trace it back to about 2 million years, more or less, from the fossil record in the Homo at the genus level. And why this prolonged lag phase? Mostly, we were in a rather primitive state, very susceptible to disease mostly, right? Injuries and disease. I mean, even on the woman's side, the average lifespan was about 50 years old. Typical woman died on her last childbirth. And so very drastic, what we would consider inhumane conditions by today's standard. But then all that changed, and it changed mostly in Europe in the upper Middle Ages and into the Renaissance period, with what is known as modernity, right? The beginning of a scientific method, of beginning to boil water and so forth. The germ theory, well, no, the germ theory comes much later. But basically, more cleaning, more attention to health in general, and it starts going into this log phase only in the past 500 years or more, or such. Then it skyrockets even more so with the Industrial Revolution and more access to energy sources, more machinery that is making our lifestyle better conditions. And so more or less for the past 300 years, we've been into this log phase that is essentially vertical by way of population growth from 500 million, less than 500 million, all right, so 500 million or less, 500 years ago, let's say, to the 7.5 billion that we are today, so we're here more or less. So this upper part is a projection, okay? It's an estimation because we have not passed the 8 billion yet, but it's projected according to this particular model, and who knows what factors are using and the complexity of the model, that by 2025, we would surpass 8 billion. I just checked earlier today, we are right now at 7.5 billion, more or less. Remember, this is the American million, which is 10 to the 9, right? So it means 7,500 million, 7,500 million people globally. And there doesn't seem to be any end in sight of the population growth. In some areas, there is some leveling off, and typically we attribute that leveling off to limited resources, okay? Limited resources. All right, so let's look at population density. Population density. Density, of course, is a composite, right, of numbers by area, by surface, just like speed, for example, velocity is a component of distance in time, per unit time, all right? So when we do the math and divide that 7 billion people, 7.5 billion people into the square kilometers of the surface of the Earth, we get approximately 51 people per square kilometer. Okay? That's a theoretic. But that is when we consider the total land mass of the Earth, including the poles, including Antarctica. And very few people actually live on Antarctica, right? Even though it's a huge continent. So this is the theoretic population, 51 persons, approximately about 50 persons per square kilometer, approximately. And I say theoretic because this would include just the straight up arithmetic of dividing the number of people on the Earth, 7.5 billion, into the square kilometers of the landmass of Earth, including the poles. Then, I had one. Yeah, let me jump here for a moment. More realistic is about double, because what does this mean? It means that approximately half of the Earth landmass is not inhabitable. Typically, they're going to be the poles. They're going to be large tracts of, let's go to Google Earth here for a moment. Oh, we might have to extrapolate from a map. Let me see if it's going to give it to me. Oh, I have to do the download. I think it's easier just to punch in an address and expand from there. Any address will do. We click here. And then we go to the satellite view, which is down here. We get rid of this particular farm. And there we have an image. Okay, so these are satellite images. which happened to be Carol City somewhere. Okay. So, okay, let's, since we're zooming out of Carol City, we're near our place. That's I-75, trace it down. Diamond Springs, okay. 826 is the Palmetto North, right? There's a green patch, St. Thomas University. Okay, so this is a forest, you recognize it, right? Einstein Brothers in the middle of the forest. Supposed to be over here in the library. All right, it's approximate. Then you can use the smell. The smell. Yes. Once you go to the property, you have to smell the coffee. All right. See how interesting the patch of green is surrounded by urbanicity and even an airport, the Opelika Executive Airport and so forth. So nowhere else nearby until you get to the Everglades over here, west of I-75, do we find a patch of green like that we have here at the university. Still there.
Yeah.
Look at that, still there. Yeah? Look at all the gray around it. Okay. Now, South Florida, the Keys, the Caribbean, the Gulf of Mexico, Earth, right? Oh, with weather. Okay. Yeah, isn't that amazing? Okay, and look at this. This is what we can do. So, of course, this guy is not available. The North Pole, which they have excluded from here, they took out the ice cube of the North Pole, is not available either. All of these northern territories, you realize, by the way, that Canada is actually larger than the US by territory. The boundary, the frontier would be around here somewhere. Oh no, there it is, sorry. Yeah, but it's actually larger, see, by territory. So Canada is underpopulated. I forget the actual, how many millions, but it's very underpopulation. Most of the population of Canada lives along the border here. It's so funny to watch these population diagrams, political geography, because they all live on the southern border here, close to the US, because the rest is so cold that it's uninhabitable. And this whole area known as the Northern Territories, huge tracts of forest, of coniferous forest, and then the tundra region, this tundra, not very inhabitable, super cold. So when we start taking out chunks like that, when we take out, of course, yeah, the Amazon is another one, right? Very low population density. There's some population, mostly the natives, but low population density. Of course, look at the Sahara, very uninhabitable, and it's expanding, sadly. Yeah, it's amazing, but it's very big. There it is. So look at what's left of Africa. This is the Congo, the Democratic Republic of Congo, the DRC, the other lung, right? The tropical rainforest. Arabian Peninsula, of course, again, another desert, uninhabitable. Then Antarctica, which good thing they left it because it's a continent, uninhabitable. The center of Australia, which is also a continent, smallest continent, right? Center is basically one huge desert, uninhabitable. So when you add all that up, it's about half of the world, half of the landmass is uninhabitable. And that's why that first simple statistic of just taking the number of people on Earth and dividing it by the total landmass is not realistic. More realistic is to cut it in half, more or less, half of the world uninhabitable, or only with very sophisticated technology. So it's never going to be very high density in those areas. Okay, now we can go back here and try to project that into our land, our terrain. Like I say, it's about I said 120, I think it's about 160 acres total. Anyway, we have 700 by 800 meters. I'm putting it in a decimal scale, all right? This is 100 meters here, as you can see on the scale. Probably. That little number is 100 meters. So that's the scale. Those are the bars that I use to just to segment out and figure out what is our surface area on campus, because as you drive through, you get a feel for what is the size of the campus, more or less, right? Now we project the theoretical population density. I put these guys here on purpose to show, make kind of a random distribution, more or less, all right? And this is what it would look like with the theoretical population density, but not of the 51 per square kilometer. We have about half a square kilometer on surface, so it's about 29 people, okay? It's half of that, all right. But in reality, the realistic, right, it will be double. So it really looks like this. So instead of that, is that.
More like it.
Yeah. So this is starting to look a little more dense to the eye, right? Of course, it's disproportionate because these are huge human beings, right? These are huge, these are giants. But just that's more or less the density that would be worldwide if we were evenly distributed. But we're not evenly distributed. Even on the populated area, in other words, on the inhabitable area. On the inhabited area, we're not evenly distributed. And I give you a simple example. Let's say we're flying, all right, and we look out the window and we're on top of land and not sea. What do we see? We see mostly green, all right? And the green is either going to be native green, in other words, forest, grassland, whatever, wildlife, or it's going to be agriculture, okay? And it's mostly just vegetation. And then we see areas of concentration of population density. So we start trying to get it more realistic of where the bulk of these 7 billion people live, all right? Is mostly in urban areas. And that's why we get these kind of maps. Because even so the gray is uninhabitable, right? The gray is kind of uninhabitable. This is Siberia, way up here, equivalent to the northern territories of Alaska, including Alaska, but Canada. There's Greenland, the Sahara, you can see here. But then this is the density map that is mostly in the temperate region, even into the subtropical region like India, subcontinent, and Southeast Asia. All this area, this is the largest population density of the world, right? Between India and Southeast Asia. Then Europe is pretty densely populated, on average 4 or 5 times more than us, for example, here in the US. And then the coast, you notice a lot on the coastline, especially in the Americas, the West Coast and the East Coast. All right, the center, the Midwest, for example, rural, and also, like you mentioned, the basin, the Amazon, there's the Amazon, pretty much paralleling the equator, warm and humid. Okay, so these are the numbers. That's what it would look like on our, but it's clustered. In other words, it's not an even distribution, it's very clustered. So we go back to this thing, about half of it is inhabited. And now, we look at megalopolis, okay? This is actually an old number. I need to correct this because I checked today. And so by definition, a megalopoly is a city or an urban area that has more than 10 million people. 10 million people. And I checked, it's up to 45 cities in the world. This number, by the way, number of cities is growing exponentially. It started obviously as 1 or 2 or 3, all right? And now it is beginning to increase, but not linear, exponentially. These megalopolis that have more than 10 million people, some up to 30, 35 million people.
30,
So,
35?
exactly, million. Population density, okay? I'm going to show you, we're going to do a little math here, so arithmetic that I didn't have time to finish because I was getting the new numbers. No, this is just, sorry, let me go to this Excel. All right, so what do we have here? We have the number of cities and their population density. Just those two columns for now, okay? No, not population density, in absolute numbers, number of people. Yeah, millions of people. Okay, it's the largest. It's called Tokyo, Yokohama. It's a whole huge urban area. There's Mount Fuji, okay? It's a huge urban sprawl that goes over several towns, several cities that have been clustered together, similar to us, but in a much smaller scale. How you're on 95 and you can go between Miami, Fort Lauderdale, Broward, up to Palm Beach, and you can't really tell when one county ends and another county begins because the urban sprawl has spilled over the county lines, right? And it's just one big urban area. So that's the phenomenon that we're getting. Mumbai, that used to be called Bombay in India. Beijing, that used to be called Peking, right? All right, that's dating me. So these are the numbers. And goes down different parts of the world, mostly Asia, Africa, some in Europe, some in Latin America, some North America, all the way down to number 45. And the total, when we add this is the grand total, is just under 1 billion people. Under 1 billion, one of the 7 billion, 1 billion of the 7 billion live in these 45 cities. Now imagine how many thousands, hundreds of thousands of cities there are in the world. And only 45 cities in the world hold 1/7 of the world's population. That gives you an idea of density, of urbanicity. So what do we see? We can detect some behavior. Here, we're a very social species. We like to cluster together. We don't like to be out in the boonies, right? In the rural area, farming and stuff. No, that's for the birds. We want to be in the city. Exactly. We want to be in the city where the lights are and the discos and the infrastructure and the internet and everything is accessible and available. But then to a point, because when you start getting high density, then there's going to be some negativity. All right? We have higher crime, higher violence, higher addictions, higher everything. And the infrastructure to maintain that, higher traffic, higher exasperation, higher rate of heart disease and cardiac arrest because of the stress level. More stress. So where's the balance for the human species? You know, it's not known, but generally we can say that generally, like in suburbia, right, where you have some benefits of the infrastructure that is helping urban density, of urbanicity, but at the same time, there's enough green space around so that we're not just literally on top of each other, like it would be, for example, Brickell is becoming that way. These little downtowns are being generated throughout the city. In the southwest area that you're familiar with, for example, around Dadeland, all these high rises, high urban thing there, urban density. So we have to be careful because it's a balancing that has to occur. Anyway, I put next to the cities here the square kilometers for each city, all right, in this column C. Actually went in and pulled out the square kilometer for each one of the cities or metropolitan area. They're typically in the range of the thousands of square kilometers. That's the range there. And so I didn't have time to finish it, but what I want to do now is I want to add these square kilometers and see how much we get. 4 square kilometers. Let me open this for a moment, pin it, and get an auto sum here. Okay, so that is the square kilometers. And now we can look at the now we can look at the average density of the 45 megalopolis that exist on Earth, right? Which we would do what arithmetic.
Those are square kilometers?
These are square kilometers, exactly. The square kilometers are about 500,000 square kilometers, okay? That is the sum of this column here that you can see. And the scale here is square kilometers for each one of these cities or metropolitan areas. So now we have a grand total of the square kilometers of all the megalopolis in the world so far that are 10 million people or more, and the grand total of those millions, which is this 800 million, right? Now we can do a little math here, a little arithmetic. We want to find the density, which is going to be the number of people divided by the square kilometers, right? And that's the population density. So 1,500 people per square, 1,600 people per square kilometer, right? 1,600 compared to the average for the world that we had set on the realistic. Forget about theoretical, it's not realistic. On the realistic, it's 100 people per square kilometer. But the sum total of these megalopolis, their density is 1,500, so it's 1 order of magnitude more. It's 10 times more, the density, right? We can also do another little calculation, which would be this. I'm going to do it over here. So this is density. Over here, let's see what percentage is, well, let's look at the population. What percentage is this of the world population, right? And it was
7.5 billion?
Right, world population. Let's look at a little more precise. Okay, 7.53 billion. So let's use that number here.
So it hasn't been calculated yet.
7.53 billion. Do I have enough zeros? This is world population, right? And now we can do the other one to find out percentage. So this is going to be equal to numerator divided, times 100, right, to get a percentage. Divided by denominator, the world population, 10%, approximately almost 11%. This is percentage of megas. In other words, this is a percentage, let's round that up. 11% of the people of the world live in 45 cities, okay? And we can also do something here. Let's put, let's put here the total surface of the Earth, habitable. Habitable surface of Earth, 57 square miles. We need that. Okay, we'll translate it to kilometers in a minute, square kilometers. Let me see. This is the total, but we need half of that, which is, I think it's this number here. Or inhabitable, about 57% from the total land area leaves habitable land. Okay. So we need this number translated into kilometers. Move this around for a moment. No. Miles in, this is square miles, makes a difference. Square kilometers. Okay, let's just stick with the, oh, give me the whole thing. Now we can copy this number here. This is the square kilometers of Earth that is inhabitable. Now we can see the percentage, what the percentage represents of those 45 cities. So we say the same arithmetic here. We need the numerator is the number of square kilometers of the 45 cities times 100 to make it a percentage divided by the total of inhabitable land on Earth. And that's the percentage. And that's percentage, it's less than 1%, all right? Exactly. So this is percentage cities. Surface. So we can say that 11% of the people of the world live in less than 1% of the area of the world. What we did here, Dr. Claudia, is this is the total number of square kilometers of all the 45 megalopolis. Okay, 500,000 square kilometers. I'll add the units here and send it to you more complete, basically just to do the arithmetic. 500,000 square kilometers is the sum total of the 45 megalopolis. This other number here is the total, let's put some commas, is the total surface area, inhabitable surface area of Earth, that 57% more or less. And so we did the math here. This is the percentage of the inhabitable surface of the Earth that is occupied by the 45 cities. See, 0.8, meaning less than 1%. Those 45 cities take up, right? So this is very high density. 10%, over 10% of the people of Earth live in less than 1% of the surface of the Earth. Very disproportionate. So all this to say that periodically you hear the argument of overpopulation of the human species, right? And you have to say, well, it depends. Are you talking about overpopulation of the world as a whole? Not at all. So we can do this other number, for example. Let's look at this other number. Well, that density, that's going to come to 107 people per square kilometer, more or less. It should. We take number of people of the world divided by total surface. Yeah, there's 117 people, 118 people. Average density of the planet. So all this to say that a lot of people are living in very crowded areas, okay? And then the rest of the world is not that densely populated at all. But the general tendency is a movement, it's a migration. Is it from urban areas to rural areas or from rural areas into urban areas? The general tendency is to go urban. Now, for a few people, after being urban, we get tired of it and now we want to go rural. But it's a lesser number of people, and typically it's the people that have greater means, because when they go rural kind of in style. They're not going to go back to farming, to milking cows and things like that. You know, they'll go into luxury areas that are low density and so forth, but it's the smaller percentage of the population of the world by far. Most people of the world in these high density areas, they want to move to the urban cities where they have some access, but they don't have skills, they don't have anything, right? And they move into these areas, and that causes massive social problems. So when we talk about overpopulation of the world of humans, and that we're causing all these problems, and including possibly the next mass extinction that may be on the horizon, which I'll cover next week, then we have to qualify it. Well, it depends. What part of the world we're talking about, what kind of cultures are involved in this, you know, and many, many factors. So it becomes a very complex question. The question of the carrying capacity, the population growth curve of the human species, or the human population, the carrying capacity, it becomes very, very regional, very regional. Now, having said all that, we can't just leave it in disaster, or, right? There are agencies that are trying to get a grip on this. One of them is the UN, with all its good things and bad things. But the UN has come up with some kind of a plan that is trying to make an impact on well-being for the human population. And they have this, first they had the Millennium Development Goals. So I have two more concepts I want to present. This one from the UN, and then finally just end up with what is the Catholic teaching on all this for the bioethics of human population growth. First, on the occasion of the year 2000, right, the UN had come up with with 8, what they call Millennium Development Goals. These were 8 goals, concrete goals, that they wanted to accomplish in 15 years. In other words, by 2015. All the member states, which is the vast majority of the nations in the world, 190 something nations, almost 200 nations in the world recognized, are represented in the UN, including the Vatican as a permanent observer. So they have an influence, but they don't vote. And it's known as a permanent observer status, the Vatican State. Anyway, this was the goal in the year 2000 to be accomplished in 15 years, to eradicate extreme hunger, to have universal elementary education, so against ignorance and illiteracy and so forth, reduce child mortality, gender equality. Here it can get a little bit ideological also, because there's ideology filtered in here by a number of groups and agendas that are pushing their own itinerary. Mm-hmm. But in principle, we can say that gender equality, when it's interpreted correctly, is a good thing. For example, equal pay for equal work, right? Why should women get paid less than men for the same amount of work? And still it happens in a number of countries of the world, many countries of the world, sadly, it's an injustice. So things like that, okay. They focused on some dreaded diseases that can be epidemic or pandemic, maternal health, of course, environmental sustainability on the green side, And partnership for development is very amorphous. What does it mean? What does that mean, etc. But it's kind of a fraternity of humanity that we're all in this together, and to try to come up with common plans, right? Well, these goals were not met by 2015, sadly, but they weren't to some extent, but it was too ambitious, really. So now they extended, and now they have tweaked it a little bit, and now is sustainable development goals, being refined and so forth, and they projected it out to 2030, and they kind of doubled the goals. So it became more ambitious in a longer span of time, but to seek it more aggressively, and also with the expanded number of goals, more than twice, from 8 to 17, a lot of these goals also became ideological. Some were split into different sections, but rather ambitious and bold, like not to eradicate extreme poverty, but no poverty, okay? And no hunger as separate goals. They're just a little more bold, etc. But these are, in principle, things that we can all agree that are worthwhile. For example, access to technology and infrastructure and so forth for the world. Why should we have internet and people elsewhere not have internet, right? Many times it's government controlled and things like this, because not everyone has a democratic regime. Anyway, so now we have 11 or 10 years, 10 and a half years to accomplish this, double the amount of goals, again, ambitious. So it's very complicated for sure, but it all comes from this human population growth, the fact that we don't know what is the carrying capacity of the Earth, but there are hints that we're kind of hitting the limit in some areas. And a lot of it has to do with industrialization, and back to the fossil fuel thing, that we need to do better than that, really, at some point, okay? Now, I want to finish with what would be the church teaching, Catholic contribution of this. And we can intuit that the Catholic contribution is going to be a challenging one. And I'm going to go back to this curve. Because what is a Catholic take on this curve? Should we be doubling the population at every generation, every 20 years? Right? Responsible parenthood. In other words, not Planned Parenthood, which is the largest abortion industry in the world, International Planned Parenthood Federation, IPPF, which is very strong here in the United States and many other parts of the world, and is also promoted by the UN and everything else. I'll put it on record because it's the truth. We're not talking about Planned Parenthood, we're talking about responsible parenthood, which is the catchphrase of Mane Vitae, Saint Pope Paul VI, 1968, with that first family encyclical, if you will, after Vatican II in the 1960s, here for us in the Catholic Church. And what he's saying is that parents should only have the number of children that they can reasonably maintain and so forth. So the two extremes to avoid are obviously a contraceptive mentality, whereby children are seen as an epidemic, as something to avoid by all means possible, and I literally mean all means, so that when the contraceptive fails, get the abortion. That is obviously to be avoided. It's an extreme injustice on many levels. But the other extreme is also to be avoided. In other words, men have not been created to go around fertilizing all these women as a bumblebee goes through flower and flower and flower, okay? That really needs to stop, because that's totally irresponsible. And it has to be on both sides. Men have to really live much more maturely than just going around as if they were the alpha males on a population, which is going to be the world population of females. Totally unfair and unjust and irrational. And women also have to do their part and not being convinced or not giving in to these men who bamboozle them for whatever reason into having very irresponsible intercourse, and therefore increasing this world population, especially in the developing countries of the world, as we see this, because when we go over here back to these 45 megalopolies, and I can expand these cells. It's a nice thing that we can do with Excel. We can manipulate a little bit here. For example, I take the column of continents, and we can sort these continents. Expand. And we can see that of the 45 megalopolies, 2 are in Africa, but then the other, let me do a little ranking here. Just to see how many are in Asia. Oops, 3 are in Africa, sorry. Let me change this for a moment. And let's just scroll down. Let's see how many are in Asia. 31 of the 45 are in Asia. So only 3 are in Africa, even though Africa we typically associate with high density population, but they also have a high mortality rate. Okay, and so only 3 are in Africa. 1 in Nigeria, 1 in Egypt, and 1 in Congo. Okay. But then 31 out of the 45, which is 2/3, right, are in Asia. 1, 2, 3, 4, 5 are in Europe, 4 in North America, 3 in North America, and 3 in South America. Okay, so that gives you a distribution. Then you can play with some more and see which are of Asia. What's your guess? Most of them are going to be China, right? Most of the Asia are going to be in China, and the rest are going to be in India, Korea, Philippines, etc., but scattered. But China takes the bulk. Overall, China. Then when we translate, again, I'm making very, very big generalizations here, but China is one of the least Christian countries in the world. They have other religions, but basically I think it's less than 1% of the Chinese population is Christian. To try to present an anthropology that is a family anthropology, that has responsible parenting and so forth, at least in its tenets, whether then it's played out or not, it's lived, we have to go family by family and individual by individual, but at least in the tenets of the religion is built in this responsible parenting, right? So that would be the church's solution to this population growth, which a lot of it we can intuit is just irresponsible. But it requires the human will of living a very mature marriage. First of all, to be married validly for life and all that, only one spouse for a lifetime already. If we were to reduce it to that, to one spouse per lifetime for each couple that is out there, that would drastically reduce the number of births in the world. It turns out that at the population level, what we're noticing, what we're experiencing, what we're observing from the human population, that we're behaving like most other mammals, which is the typical pattern, reproductive pattern in mammals, is the herd. In other words, one alpha male with several females going around so that there's going to be at least one female that is pregnant, at every time. So there's a large production, relatively large production of offspring because it's geared precisely for, in nature, it's geared for reproduction, right? For the offspring. But what I'm trying to say by all this is that we're really behaving no different than the rest of the mammals on Earth, okay, at the instinctive level. In other words, the will, reason and will are not really kicking in as they should be for the human. So we have a long ways to go, and this to me is the bottom line biological issue. How to behave more human and less animal. That's basically the crunch of what our solution would be to this population growth. In addition to the issue of the megalopolis, that it's extremely complex, but also from our perspective, and this is now the pure Catholic teaching, since we believe that we are created in God's image and likeness, and it's associated precisely in Genesis. The image and likeness is also associated with male and female, he created us. So somehow it's associated with our sexuality and our proper and improper use of our sexuality, right? In principle, we have the capacity to behave responsibly. Whether we actually do so or not is a different story, but at least we do have the capacity. We don't have to live like animals, in other words. We don't have to live just like other mammals do by pure instinct. Mm-hmm. And so that would be the bioethical solution. But of course, it's a very, very high standard, right? Very high standard, because most people in the world, sadly, we can intuit, are not following a standard of restraint and responsibility, everything that is involved, the maturity that is involved in the proper sexual expression of humans. Okay, so basically this is what I have. Now we have to leave it again open-ended because this issue of world population growth is so complex, involves human behavior and trying to convince people to act responsibly. I would say also that's why you see the Catholic Church placing a lot of emphasis on the youth today, to try to get them educated so that they live their sexuality responsibly precisely before they start acting out on it in the teen years. Okay? And that's why we place a lot of emphasis on Catholic education and so forth, elementary schools, high schools throughout the world. In fact, to this day, I would say that one of the best schools to go to attend to throughout the world are Catholic schools, right? Because of the good, solid value education that we tend to receive in these places. But it's the value system that we try to promote. It's an ongoing task. It's a very open-ended task. But I was saying, Dr. Claudia, the emphasis that the Catholic Church is placing on the youth in the world today to try to educate them with values, with moral values, not just a, let's say, like an academic or a secular education of being very proficient in whatever skills they develop, but actually the value system, how to behave responsibly so that we don't end up living like the rest of the animals and causing these issues that we're going to look at in the next lecture. All right? Yes.
But isn't also that in this metro megalopolis
Yeah.
that people, the new society is also going the extreme where couples now they're avoiding and they don't want to have any children.
Yes, indeed. There's a lot of pressure, especially in the civilized areas of the megalopolis, to avoid children because they're an inconvenience. And it's again, it's complicated. We have to be careful with blanket statements because people say, well, the younger generation, they tend to be more selfish and such. But we have to be careful. I guess from our perspective as older folks from previous generations, we had kind of a different value system and more family oriented. We see that the younger generation tends to be more technology oriented, efficiency oriented, and things like this. And so the children can get in the way, right? And so there seems to be a general trend now, but mostly in the developed countries, to avoid children. Okay, for the young couples, they'd rather have their high-rise flats and their vacations than have their children.
Or a dog.
But it also, it has been
Or,
A pet.
a pet.
or a pet instead, yes. That is happening in certain cities
Yeah.
where the pets have become the substitute for the children. Yeah, that's
And I
again
think-
another extreme, very, very sad,
I
right?
think Father that also it grows like parallel. There's this new generation, but there's also the generation that divorces are more common. They get
Yes.
tired easily, so they can have one kid, but they don't get along, they divorce, and they have other couple with other kids.
With other
So
kids,
I think
yes.
that it's
Exactly. So we get in this. We get in these blended families, right, where we have
normal, divorce is
my
normal.
kids and your kids and our kids and so forth. So 3 different groups of children that are intermingling with each other, and they're half siblings and so forth. And so even the family is being redefined. As we see, a lot of social agendas and issues are going in there, ideologies that are not necessarily Christian at all. And the overall picture of what we see is that the layers of complexity are increasing, right? So it's more complicated to live today than to live before in general, even though we could say that possibly the conditions of life were harsher way back, 2, 3, 4 generations, maybe half a century ago, the conditions were we didn't have as much well-being, but there was more stability in society and perhaps harmony. I don't know, the value system was more uniform. Today, everything is questioned. Everything is questioned, just for the sake of questioning it, right? And what value system is going to prevail? It's going to come down to our anthropology, our vision of the human person. That's why I started a whole program precisely with those fundamental principles of looking at a theological anthropology, at a Christian anthropology. What is our vision of the human person? And then hopefully to behave consequently. But how to present those arguments to society at large, good luck. It's a very big challenge. It is a challenge.
I think we have to try to go back to the basics, and that has to be instilled
Yes.
in our children.
Mm-hmm.
You know, otherwise, we will not change anything.
Agree. Forever is going to the basics. Now, what happens is some people question, because they're questioning everything, they're going to question also, well, what is the basics? What may be the basics for you may not be the basics for me. Okay, so maybe the basics for you is family, the basics for me is traveling. And so even that is questioned, right? And that's why in bioethics, and now this gets at the bigger picture of bioethics, we as Catholics do principle bioethics in contrast to utilitarian bioethics, which is in utilitarian bioethics, for example, the end justifies the means. So if to me, the end is to travel and see the world, then whatever it means, if it means putting aside children and going through other relationships and so forth, whatever anchors me down, I discard and I drop. But in principle bioethics, the value system is going to be very different. But my intuition after decades of being around is that principle bioethics is not the larger population, whether they realize it or not, whether they admit it or not, are utilitarian. People functionally, I think their value system, implicit value system is kind of a utilitarian. If it works, do it. Don't study too much the ethics of it, just move it forward. If it's legal, do it, right? So principle bioethics, we're always going to be like the shrimp against the current. Okay, folks, well, there it is. I leave you with the complexity. We'll pick it up again next Saturday and see, even with all this, there is something certainly that we can do and that we should try to do to better our relationship with each other and our relationship with the environment, okay? So once again, thank you very much, and I'm going to close it here, and hopefully we'll pick it up next time with the challenge of climate change.